Module 3.3, Wave Velocity. Every medium has its own wave propagation velocity. That means that waves will travel at different speeds in different mediums. Also, as long as the medium doesn't change its conditions, wave velocity will remain constant. Let's look at the wave equation. Since frequency and wavelength are inversely proportional and velocity is constant, if we increase frequency, wavelength must get smaller. So, with my jump rope, a slow shake or a low frequency makes a long wavelength, and a fast shake or a high frequency makes the wavelength smaller, since the velocity remains the same. This works the same way with longitudinal waves. Let's look at my slinky. As I move it back and forth, there are areas of compression and rarefaction. They move at a constant speed, and if we were to graph the slinky's spring density at one instant, we would see that it looks like a sine wave. As I increase the frequency, the wavelength decreases. This is similar to how sound waves travel. Air molecules get compressed and rarefied as they move away from a vibrating source. So, using our formula from above, we can determine the speed of sound in air, or in any medium for that matter, if we know the frequency and the wavelength. There are a number of formulas for determining the velocity of a wave based on the properties of the medium. For solids, the formula for calculating velocity of a wave is v equals the square root of E over rho, where E is the elastic modulus, or the stiffness of the solid, and rho is the density of the solid. The big picture. In a solid, velocity increases as the substance gets stiffer and decreases as the solid gets denser. By the way, we won't be talking about solids in this course, so you do not need to learn this formula. For gases, the formula is V equals the square root of gamma RT over M. Gamma and R are constants, T is temperature, and M is the molecular weight of the gas. The big picture. For gases, velocity is directly proportional to temperature and inversely proportional to molecular weight. Now, we've dealt with the square root issues before, and you know that it makes things a bit messy. However, in this formula, T is absolute temperature, referenced to absolute zero, where all molecular motion stops. And we are mostly interested in sound and air, so we can turn a bunch of the variables into numbers. To make a long story short, it turns out for the temperature range where we humans can survive, we can make an approximation for velocity in air that eliminates the square root sign. So the formula for the speed of sound in air is V equals 331.3 plus 0.06 T, where T is the temperature in degrees Celsius. The answer will be in meters per second. So in this course, we will not use the square root formula from above. The big picture? The speed of sound is directly proportional to temperature. So the hotter it gets, the faster sound travels. Please note, from now on, if I give you a temperature, you are expected to use this formula for the speed of sound. If I don't give you a temperature, the speed of sound in air is 343 meters per second. Finally, for waves in a string, velocity equals the square root of T over mu, where T is the tension and mu is the mass per unit length, or linear mass density. Mu is measured in kilograms per meter, so you can think of mu as the mass of 1 meter of string. The big picture. The velocity of a wave in a string increases with tension and decreases with the thickness or weight of the string. We will spend a lot of time with strings, so you will need to use this formula. And now, an important message from your professor. At this point in the course, you already have several formulas for frequency, and there will be more. We now have a few formulas for velocity. Make sure, as you are solving a problem, that you determine which formula to use. For example, the velocity of a wave in a string is not the velocity of sound in air. So make sure that if you're doing a string problem and need velocity, use the formula for a string. Do not use 343 meters per second. If you were observant, you may have noticed one common thread in all of these equations for velocity. Density or weight was in the bottom of all the equations. So with this information, we come up with one final big picture. Wave velocity is inversely proportional to density. The denser an object, the slower a wave will travel through it. This applies only to mediums that are similar, that is, for comparing solids or for comparing gases, but not for comparing solids to gases. To review, wave velocity is determined by the medium the wave is traveling through. For a particular medium, velocity is constant, so as frequency increases, wavelength decreases, and vice versa. In air, the speed of sound equals 331.3 plus 0.06 t. The speed of sound in air is directly proportional to temperature. For waves in a string, velocity equals the square root of t over mu. Velocity is directly proportional to tension and inversely proportional to linear mass density. In all mediums, velocity is inversely proportional to density. For string problems, velocity is not 343 meters per second.